Okay, here we go, folks. Let me get your attention. Let's get started here. So 2.3, asked you to look this over. Let's see how you did. See what you remember. We're going to take some notes down at the bottom, and then we'll kind of come back up to this. So zeros. Zeros are x values that make a function equal to 0. All right, this is one of the better math terms that I think they've come up with. Like the name actually matches what it does. How do you find zeros algebraically? Do you guys remember? Yeah, so y equal to 0 and solve. Now this whole process is made a little bit easier if they give you the function in the form of a not a fraction, but factors in a factored format. So if it's factored, then what do you do? Well, you split it up, set each of those factors equal to 0 and solve. So in the example up above, we had a bunch of factors, and that's how we're going to find our zeros. We'll get to that in a second. But while we're here, let's talk about where we find zeros on a graph. Where do we look on a graph to find zeros? Across the x's, so x-intercepts. But it's actually possible to have zeros that don't correspond to x-intercepts. I'm not sure if you guys would have done this last year or not. Did you deal with complex zeros last year? Zeros that had like an I in them? Imaginary zeros. And imaginary zeros aren't going to give you an x-intercept. So you will see zeros as x-intercepts as long as they are real. So I'm going to write unless complex. Complex would mean something with an I in it. So we will end up, not today, but next week we'll be dealing, and we'll do a little review on imaginary numbers before we get into it, but we'll be dealing with complex zeros, and those don't cause x-intercepts. Only real zeros do. Today, all you're going to see is real zeros, though. So let's go back up here and find our zeros. So my factor here is x. If I set x equal to 0, I'm going to get x equals 0, solve that, and get 0. That one's easy. Set x minus 2 equal to 0 and solve, and you're going to get 2. X plus 5 equals 0, solve that, you get -5. 2x plus 1 equal to 0 and solve. Are you guys comfortable just coming up with -1/2 in your head without showing work for that? If not, you're allowed to write 2x plus 1 equals 0 and subtract 1 from both sides and divide by 2 on both sides. If that helps you to get to -1/2, then do it. But if you're able to skip all this and just jump straight from the factor to the 0, I'm fine with that too. All right, so those are our zeros. Going back down to the bottom now. Multiplicity. So when we're looking at a factor, if the factor has an exponent on it, that means that factor is included more than once, then that's going to give us multiplicity. If the exponent's 1, it has an exponent or multiplicity of 1, so on and so forth. So when I look at this x squared, because of this exponent of 2, my multiplicity would be 2. X minus 2 is a factor. It does have an exponent on it. We don't usually write it when it's a 1. So it has a multiplicity of 1. What's my multiplicity when I'm talking about the 0 at -5? It has a multiplicity of 3. And this last 0 has a multiplicity of 1. All right. All of our zeros are real, which means we're going to get an x-intercept for each of these. The only difference between a 0 and an x-intercept is an x-intercept is a point. So when we write it, we need to write it as a point. 0, 0. If the 0 is 2, then you're going to have an x-intercept of 2, 0. So just change all those zeros into points and fill in that row if you haven't already. All right, and then one final piece is the behavior. I'm going back down my screen to behavior. So when we're talking about behavior, we're talking about what happens when the graph crosses the x-axis. What's happening at that intercept? And the two basic ways that this can happen is either the graph is going to cross over from one side of the x-axis to the other, which is what I'm showing in these first three. That happens whenever you have an odd multiplicity. Now, sometimes it does a little, what do we call this? A little swoop while it does it. But it is still crossing from one side to the other. On the other hand, if your graph goes right up to the x-axis, hits it, and then bounces off of it without crossing over, that we call bounce or touch, and that happens when you have even multiplicity. Now, this won't become that important until next week, but when we start looking at graphs and writing equations from graphs, there are some ways to tell whether you're dealing with multiplicity 1 or a higher odd multiplicity, and it really has to do with like how much of a swoop it makes when it makes that cross. Is it crossing straight over? If it's crossing straight over like this, then you're looking at multiplicity of 1. But if it kind of flattens out at the x-axis, that's probably multiplicity 3 or 5. It gets really difficult to tell the difference between 3 and 5 and 7, and I don't expect you guys to be able to look at a graph and tell that or anything like that. So a little more information here than we're actually going to use. The big thing is it's going to cross when you have odd multiplicity and bounce when you have even multiplicity. So let's look at our multiplicities up here and talk about the behavior. So when we draw our graph in a minute, when we go across this x-intercept, are we going to cross or bounce? We're going to bounce. We have an even multiplicity, so we're expecting to see our graph bounce off of the x-axis here. This is an odd multiplicity, so at 2, 0, we expect to see our graph cross the x-axis. Same thing at -5, 0, because that's also an odd multiplicity. And also at -1/2, 0. So we got 3 places on our graph where the graph is going to cross the x-axis, one where it's going to bounce. And what I'm expecting to see when I do graph this is that when we cross at -5, we're not just going to cross it, we're going to kind of make a little bit of a swoop as we cross it. We're going to sort of flatten and make sort of an S shape. All right, we almost have enough information to hand draw this graph. The one missing piece is the end behavior. Can you guys set up your end behavior for me in this little space right here with that limit notation? See if you can remember what that looks like. You did a little bit of that in your practice work for Tuesday. I'm hoping that as we're seeing this over and over again, that we're able to write down the format pretty quickly. There's a shortcut for knowing what the end behavior is going to look like for polynomials. And it has, there's a little dance I'm gonna teach you. It's gonna be super awkward, guys. Yeah, it's gonna be awesome. And and just in time for homecoming too. And I'm not gonna be there, but I know some of the chaperones, and I expect to get a good report about people doing the end behavior dance. Now, in order to do this, we need to know what the lead term of our polynomial is. Do you know what I mean by lead term? Like the highest degree term, like if it were all multiplied out, but this isn't not multiplied out. So do we need to actually multiply the whole thing out to figure out what the lead term is? There's a shortcut for this. We can just multiply all of the high terms in each of our factors, and that'll give us our lead term. So let's build this up. So I got x squared times x. So I'm at x to the third, agreed? Times x, but keep in mind this x is included 3 times. So what am I up to? We're 6. So x to the second, x to the third, x to the 3, 4, 5, 6, and then x to the 7th and a 2. So my lead term is going to be 2x to the 7th plus, and then I don't really care what the rest of it is right now, anyways. All right, so I'm just trying to figure out if I were to multiply this out, what would I get? And I did that by multiplying each of my lead terms here, keeping in mind that this one is going to get multiplied 3 times. So 1, 2, 3, 4, 5, 6, and 7, and also a 2. So we get 2x to the 7th. We okay with that? All right, so then we just need to know what the rule is. So the rule is, well, let's do the dance first. Okay, so we're going to start off with positive lead coefficient and odd degrees. So your arms give me a flat function right now. So you can, because we're all going to do it, right? It's going to be awkward. Oh, you can't do it. I'm sorry. Okay, you can just do the one side. Okay. All right, left-hand side is going down, right-hand side is going up. So this is positive lead coefficient, odd degree, okay? Now what happens when we put a negative coefficient in front of that? It just flips over. Now on the right it's going down, on the left it's going up. All right, so flip it back to the positive lead coefficient. All right, now if it's an even degree, then it's both up, right? Like a parabola, even degree, and then an even degree with a negative coefficient, down, even degree with a positive coefficient, odd degree with positive coefficient, odd degree with a negative coefficient, even degree with positive coefficient. You get the idea? Okay, so that's the dance. I expect to see a report. I don't have a song for it yet. No, they should probably write a song for it. So odd degree, positive lead coefficient, down on the left, up on the right. It can do all kinds of wiggly stuff in between, but that's what it's going to look like at the ends. Really, it's kind of what's going on the far left and the far right that matters. You change it to a negative lead coefficient, it just flips upside down. Now it's going up on the left and down on the right. Again, doesn't matter what's going on in between. Even degree, if it's a positive lead coefficient, it's up on both sides. And then odd degree or even degree with a negative lead coefficient is down on both sides. So that's our first pre-calculus dance of the year. We're going to learn about asymptotes, the asymptote dance later on this chapter when we get into rational functions. So let's talk about our function. It is even or odd degree. Odd degree with a positive or negative coefficient. So what's that look like? Like that, right? Yeah. So we know that this is going to go down on the left. I'm going to do this in, yeah, we'll do purple. Down on the left and up on the right. I know that's my end behavior. Down on the left and up on the right. Let's go ahead and fill out our limit notation before we finish up the rest of our graph. So we're going up on the right, or up on the left here. And I did that backwards, didn't I? So I've been trying to do the dance backwards to match you guys, and that's messing with my head. I know, it's terrible. So down on the left. I actually do have a little bit of trouble with my left and my right. I have since I was a little kid. So I don't know. Some people, I know it doesn't work for me. This one makes the L. That's my right hand. That's what I'm doing. I'm messing with you. Yeah, it's the one with the L. Oh God, dude, that's awesome. I've never seen that. Oh, I don't have a left hand. All right, down on the left. So this is to the left. So this should actually head towards negative infinity, right? Negative infinity. And then my y is going down. It's also negative infinity. And then for this arrow, we're heading to the right. So x is heading towards positive infinity. And it's going up. So y is also heading towards positive infinity. All right. So that's important because what we're going to do now is, well, let's draw our x-intercepts because we know we're going to have points on the x-axis at 0, 0, at 2, 0, at negative 5, 0, and at negative 1/2, 0. And those are the only places that our graph is allowed to get anywhere close to the x-axis, right? That's the only place that we're going to approach the x-axis. So what we're going to do now is, if you would follow along with me, go ahead and put your pencil down right at the end of your arrow right here. And we're going to make a nice smooth curve that is going to go through all of those points that we just drew. And it's going to eventually end up over here. Okay, now on some of those points, we're going to cross over the x-axis. Some of them we're going to bounce off of it. So as we head towards negative 5, are we going to cross or bounce? Cross. Okay, so let's make our graph cross over at negative 5. And then we're going to keep moving to the right. And as I go towards -1/2, we know we're going to have to kind of come back down to come up over to our x-axis. And am I going to bounce off there or cross? We're crossing at -1/2. And then as I move towards 0, I need to come back up. So I got to turn around and come back. But at 0, we're going to bounce off. So whoop, bounce off. And then we're going to keep heading over. And at some point, we're going to need to turn around and start heading back to the x-axis to meet up at 2. And at 2, we're going to cross again. And that's good because that gets us onto the right side of the x-axis to meet up with our other end behavior. And there's our graph. Isn't that cool? We're gonna be doing this when we get to rational functions too, but then we'll throw in asymptotes and what's going on. Are the asymptotes doing this or this? So that'll be the other dance move. Stay tuned. All right. I want us to practice a really important skill that we're going to need later on. It's not super important to this, but what I would like you to do right now is grab your calculators. Go ahead and type in this equation in y1. And I want you to graph it, just to kind of verify that we're seeing what we're supposed to see. Now, part of being a good calculator user is learning to manage your expectations. Do you guys know what managing your expectations means? Don't expect too much. That's what usually managing your expectations means. Don't expect too much. Now, these things are pretty smart and they do a lot of cool stuff, but they're not perfect. I know from experience, for example, that when I hit my graph button, I'm probably not going to see most of this graph. It's probably a lot of it's going to be way above and way below my screen. So when I hit my graph button, if I see a bunch of things that look like just a bunch of vertical lines, I'm not going to get freaked out because that's what I'm expecting. Because I've done lots of these before. So hopefully you won't get freaked out either when you hit the graph button and you see what looks like just a bunch of vertical lines. And we can't really see what's going on with that. So what I want to practice, because this is an important skill that we're going to use throughout this whole year, is let's set a window where we can actually see the important features on this graph. So I'm definitely going to need to raise my y max, because there's a hump up here someplace, and I'm going to need to lower my y min. And the key to success on this, to not spending a whole bunch of time guessing and checking, is what? What do we want to look at to give ourselves a hint about how high up and how far down we need to go? Let's look at the table. Now, before we do, notice that this hump that's going to happen is happening somewhere around an x value of like -2 or -3. And this other one over here has happened somewhere around an x value of 1. So look at your table. And notice at -2, -3, we got some pretty huge numbers there. My y values are like 1800 here at -3. So I'm thinking that we need our y values to be able to go up above 1800. I'm thinking 2000 maybe would be a good place to start. And then while we're here, let's look at how low it goes in that valley between 0 and 2. It looks like it's going down to like -650. So I'm thinking maybe I'll send my y value down to -1000. That should be enough, right? So now I'm going to go to my window and I'll change my max and min for my y values. So I said I was going to make my y's go down to -1000 and go up to +2000. And I'll graph it again. And again, I'm managing my expectations because it's probably going to give me a better picture, but it may not give me the picture that I want. I may need to adjust still. So I'm seeing the hump, but ooh, we missed that valley. We didn't quite get there. That's okay. We'll just go back into our window and modify. We made it go down to -1000. What should I try? Second go. Just barely. So maybe like -1500. 1200 is probably enough. I'm going to go 1500. All right. So now I can see all the way to that max and that min. And if I needed to find the max and min, I could. All right. So I just wanted to practice that. Because that skill of figuring out how to set your window to show everything is going to become pretty key later. Okay, set those aside for right now. And let's flip over on the back. You guys are doing awesome. Let's keep it going. This next example is basically asking us to do the same thing as what we just did, except I didn't give you a table. We'll make our own though. What else is different about this one from the last? Not factored. Okay. So let me take a minute and give my little soapbox speech here. You've heard it from me before. If you are not a strong factorer, let's fix that here like now, like this weekend. Let's get after that. You're going to be factoring so many things in this chapter that if you can't look at a trinomial and get it factored within like 30 seconds or so, you are going to struggle in this unit. Okay, you're going to spend way too long doing this factoring stuff. So either make an appointment with me, come in and see me, and I'll walk you through it. I'll give you some practice that you can do, or use some of those online resources. Has anybody ever used Khan Academy before to like look stuff up? It's pretty okay. I mean, it's pretty good. It's there's some other. Does anybody know any other YouTubers? Like I haven't really looked much recently. Of course, yeah. I've got fives of viewers. There's a woman who's she used to be an MIT professor, I think, called her handle's Math BFF, and she's pretty awesome. There's a few others out there. Anyways, long story short, like be good at factoring. Like, and if you're not, that's okay, but let's get that fixed. I don't want you guys being miserable. Okay. All right, so here we go. We're factoring. Always GCF first, right? There is a GCF here, so let's pull it out. What's the biggest thing we can pull out of all these? X squared, right? So that leaves behind an x squared minus 2x minus 35. And I'm hopeful that you can get this done fairly quickly. You could use that Xbox thing if you've really gotta. I actually kind of despise the Xbox method. It just takes too long. It does work 100% of the time, though. That's why we teach it that way to Algebra 1, Algebra 2 students, but there's faster ways. 35 is either 1 and 35 or 5 and 7. I'm pretty sure it's going to be 5 and 7. If I want it to add up to negative 2x, I want my 7 to be negative, 5 to be positive. Just checking, that's a 5x, that's a negative 7x, that'll get me there. There's my negative 35, here's my x squared, good. All right, so you should be able to factor it fairly quickly. Again, 30 seconds max for that. Actually, I would say probably more in the range of like 15 seconds for something like this. 30 seconds if there's a coefficient out in front. Okay. All right, we got enough information to make. Let's make ourselves a little table. We're going to do zeros and multiplicity for each of those zeros. Let's not bother with x-intercepts this time because it's the same as the zeros, but with parentheses. But let's do behavior. And I'm just making a sloppy, ugly table here. Should have 3 columns because I have 3 factors. This factor is x. X gives us a 0 of 0. Yeah, you set x equal to 0 and solve, you get x equals 0. Multiplicity, it's got exponent of 2, so multiplicity of 2 behavior, then it's going to bounce. X plus 5 is going to give us a 0 of negative 5, multiplicity. 1, so cross. And x minus 7 is going to give us a 0 at positive 7, multiplicity of 1 cross again. Let's do our end behavior next. So I'm going to set up my limit notation, and then we'll figure out which dance we're doing. All right. I don't know. It sounds like a food wrapper, doesn't it? We're not supposed to eat in here, folks. I do have students with pretty severe allergies. So if that is food, let's put it away, please. Thank you. All right. Hey, lead term is 1x to the 4th. So what dance is that? On the left, we're going up. Yep. So we're going up on the left and up on the right. All right, so as x goes to the left, y goes up. As x goes to the right, y goes up. And we're going to make a rough sketch. Remember, when I say sketch, it does not need to be on graph paper if you don't want to. I'm not even looking for like a whole bunch of tick marks. Go ahead and label any important values on the axes. I'd say for this problem, the important x values are 0, which I don't really need to mark that. -5, we'll go ahead and label that, and +7, we'll label that. And I know we're going to have x-intercepts at those 3 points, so I'll go ahead and draw those points on. And we'll draw our end behavior on, and then it's just a matter of connecting one end behavior to the other by going through all those intercepts and going through them the right way, as in crossing or bouncing. So I'm going to start on the right this time. Moving towards 7. When I get to 7, I want to cross over. So crossing over at 7. Then I continue moving towards 0. When I get to 0, I want to bounce. So bounce off at 0. Now I'm moving towards -5. When I get to -5, I want to cross again. That's good. That gets me onto the right side of the x-axis to meet up with my other end behavior. It does not matter which direction you go from. You should end up getting back to it. Now, if you draw your end behavior and then you do your crossing and bouncing thing, if you make a mistake along the way, a lot of times you're going to catch it because you're going to be like, I'm on the wrong side of my axis to meet up with that end behavior. And this is kind of a key piece of information. These are the only places your graph is allowed to touch or cross the x-axis, right? So if I was expecting my end behavior to be down here instead, and I got out to here, I'm like, oh, there's no way for me to cross back over here. I must have messed something up. Either my end behavior is wrong, which is the case this time, or else I did something wrong over here. No, but you should be able to start at one end behavior and finish at the other. All right. We feeling all right? Let's try it backwards. So in our next example, they're giving us zeros and multiplicities, and we have to come up with the function. So this isn't too bad. Oops, sorry. Thank you. So they gave us 3 zeros and multiplicities for each. Our job is to come up with a function. So let's write ourselves a function. And since there's 3 zeros, I'm going to go ahead and set up so I've got 3 factors. And it's just a matter of getting the right things into those factors and then the right exponents on them. So going backwards, if I have -6 as a 0, what's my factor going to be? X plus 6. And the exponent on that, multiplicity 2, so that'll be squared. A 0 of positive root 5 is going to give me x minus root 5. Multiplicity 1 means my exponent's 1. I'm just going to leave it off. And then we've got a negative root 5, so we've got x plus root 5. That would also be a multiplicity of 1. All right. All right, now we're going to multiply this out and get a standard form for a polynomial. Before we do, though, how many different answers are there for this question? It says write a polynomial that has these zeros. It doesn't say write the polynomial that has these zeros. It says write a polynomial. What could give me something that I could put in front of this that would not change any of these zeros they gave us? What could I write out here that would not change anything, but would it change with the way the graph looks? I could put a negative. Someone said a negative. I could put a minus out in front of it. That wouldn't change anything, right? I would still set these equal to 0, and I would get these same zeros, right? I could put a negative out here. What's another thing I could put out in front there? A 1 that would be the same thing, though. right? I could, but that doesn't really change anything. Give me another number that would change something. I would put a 2 out there. That would cause a vertical stretch, but it's not going to change where my x-intercepts or my zeros are, right? So how many different correct answers are there for this thing? An infinite, because we can put any number we want out here, and it's not going to change these. So keep that in mind. We're going to have to do that thing where we solve for a. Remember, we were doing that with our quadratics. We'll have to do that later on, but not today. All right, so what we are gonna practice though is multiplying this out. This is that situation where if you know some shortcuts, it will save you like dozens of minutes over the course of this year. So one of the big shortcuts that I would really love for you to know is squaring a binomial. When we square a binomial, we don't just square the first thing and the last thing. I mean, we do that, but not just that. So square the x, square the 6, but there's also a middle term in here. How do we find that middle term? 2 times a times b, or 2 times x times 6 in this situation, which would give me 12x. Okay, the most common mistake that we see when we get to the chapter test for this is people forgetting that 12x in there. Okay, you can't just square the first thing and square the last thing. This is going to come up a lot when we start dealing, especially when we start dealing with complex numbers, with imaginary numbers. Do you guys remember what it's called when we have two binomials that are exactly the same except one's a plus and one's a minus? It starts with a C. Conjugates, good. So these are conjugates. And when you multiply two conjugates together, there's a really super nice shortcut for this as well. You just square the first thing and square the last thing and put a minus in between. So square the x, you get x squared. What do I get when I square root 5? 5, and then stick a minus in between, and you got it. So we're almost there. We went from 4 factors down to 2 factors. Now we're going to multiply those out. However you want to do this, I'll show you my preferred method because I like lose things if I don't keep it organized. So I like to make a little table, and I'll put one of my polynomials across the top, and I'll put one down the side. It's kind of like the box method, yeah. And then I'll fill out my table, and then I'll do my combining like terms and write everything down. It just helps me to keep everything straight and organized. So there's a 180 in there. And then the only things I can combine are my x squareds. All right, this is all admittedly a little bit tedious, and you're going to be doing some of this tedious work. Math from time to time gets a little tedious, and this is one of those things where it's not difficult, but there's so many opportunities to make a mistake, and if you're not super careful, then one mistake turns into a very incorrect answer. So attention to detail is important, and sometimes that's really important in math too. So it's a good practice for us. By the way, I've talked about the Poly project. I'll be pushing that out to you guys next week. About half of the work when you're doing your Poly project is going to be, I'm going to give you like, there'll be like 5 or 6 factors, and you'll multiply them out to get this big like 7th degree polynomial. And it takes a while, but it's not difficult. It just takes a while. And then you check your answer with me, and I tell you if it's right or wrong, and then you move on. It's one of those things where you got to go slow to go fast. Have you ever heard that? It's a big saying in racing. You go slow to go fast. Like if you go too fast and you make mistakes, that slows you down, right? So you got to find that good sweet spot. Yeah. It's not bonus credit. It's just it goes into the test category as its own grade. So it's an extra grade that you're averaging in along with the rest of your test. No, it's optional. It doesn't hurt you if you don't do it. The only way it can hurt you is if you turn it in without checking it with me first, right? Like, because if you get a 25 out of 50 on it, I'm putting a 25 out of 50 in that grade book. But you would never do that because you would check it with me before you turn it in, and I would be like, hey, half of this is wrong, go fix this. And then you'd fix it and bring it back, and I'd be like, now only one thing's wrong, go fix this. And you'd bring, like, so if you take advantage of that, you don't wait till the last minute, then you should be guaranteed 100%. More information coming on that. All right, one last one. For this, we're going to use our calculators. So it's going to do all the heavy lifting for us. So we're going to find the zeros using technology. Do you guys remember how to find max and min? Well, there's another option in that same menu called zero, and that's what we're going to use to find our x-intercepts or our zeros. So first step, obviously, hopefully obviously, is to type it in the calculator and get it in Y1. And then manage your expectations. When you hit that graph button, you may not see what you want to see. Keep in mind, we did just stretch our graph out really far up and far down to look at that first example. So our window is all kind of wacky right now. There is a really quick shortcut to set your window back to the standard zoom level. Do you guys remember what that is? Zoom 6. Yeah. And I'm not even going to hit the graph button because I remember that we messed with the window. I'm just going to do zoom 6, and that will automatically graph it again with the normal graph window. That looks pretty good. Can't really see that hump to the right of the y-axis, but if all we're looking for is x-intercepts, I think we'll be all right. So second calc, that's the trace button, and we're going to do 0. And this is going to ask you for the same 3 questions. I'll ask you the same 3 questions as when you're finding your max or your min. Do a left bound, right bound, and guess. So use your cursor, move it a little bit to the left of that leftmost intercept, move it a little bit to the right of it, and then move it kind of close to it and hit enter. It'll think for a second. Let me zoom in so you can see the exact answer I'm getting and see if you're matching up. My calculator's doing that weird thing again. It says that y is equal to 1e negative 12, but we know how to translate that, right? What is that essentially? 1e negative 12 is basically 0, okay? That means what it literally is 1 times 10 to the negative 12th, which is a 1 with the decimal moved over 12 places to the left. Here's my 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Decimal goes here. It's that number right there. That's not 0, but like if I gave you that many dollars right now, nobody would be too impressed. All right, that's basically 0. So that's fine. The important thing is, are you getting that negative 1.726235? Yep, not something that's close to that, but exactly that value. Cool, go ahead and find the other 2. I'll put my answers up here, and if you're feeling good about that, then we are done. You can go ahead and get started on the assignment. I'll put it up on the board in just a moment. The instruction said to the hundredths, so these are all rounded off to 2 decimal places. So what we're going to focus on next week, Tuesday, we're going to be doing a Desmos activity. So make sure you bring your laptops on Tuesday. Please bring your laptops on Tuesday and your chargers. What this activity is going to look like is I'm going to give you a graph of a polynomial and you're going to try and match it. So we'll be doing a lot kind of like what we did, except kind of backwards. You look at the x-intercepts and use those to come up with factors and all that fun stuff. All right. Does anybody have any questions for the greater good? All right, let me put the assignment up here. Oops, stop.